How do you build a brand new university on a swamp?
We didn't have room for error out here.
What happens when a visionary architect is given almost 80 million pounds of high-grade steel?
They've created a 33,000-piece titanium jigsaw puzzle.
And how do you create a 4,000-ton building that moves?
When you see that there's wheels at the bottom, you say, what? How?
This is the age of the extraordinary.
It's like one of those insect-eating plants, only enormous and white.
Where ingenious engineers have unleashed unchecked creativity. Now their secrets are revealed. As we discover the inside stories of their construction.
This is an incredible feat of planning and engineering.
To try and understand, how did they build that?
Have you noticed how architects don't do easy? Like, it's not enough to design a world-class university building like no other. They then go and build it in the middle of a swamp and give it a massive pair of wings to trace the sun's daily passage around the Earth. It sounds crazy and awesome.
Florida, home to the Gators. Wrong Gators. That's more like it. Over 31% of Florida, some 18,500 square miles, is made up of wetlands, which are home to over 1 million alligators. Add that to temperatures as high as 100 degrees, and in July, it can be a fairly unforgiving place. So when they decided to build a huge new university campus on an area of swamp, it was never going to be easy.
From the beginning, we was working in a wild environment. This was a real challenge.
The design from one of the world's most exacting architects comes complete with superpowers.
This building has wings. It does take your breath away.
It was a project that would push engineers to their limits.
I knew in my mind that it had to be perfect.
A huge cathedral of architectural concrete, curving steel, and glass, with virtually no straight lines in sight and no room for engineering error. This is Florida Polytechnic University's Innovation, Science, and Technology building. So, how did they build it? Home to NASA's Kennedy Space Center, Florida is no stranger to the world of science and technology. And in the early 2000s, the state decides it needs to take that to the next level. By creating a new university focused on engineering, physical sciences, and mathematical sciences that would be like no other in the world.
We want to make sure that when the students come to the university to study engineering, that they're inspired by the architecture of the university.
The Innovation, Science, and Technology building is kind of a cornerstone for our campus. It was important to have this building that served as a little bit of an icon for us.
To create it, the university turns to one of the globe's most visionary architects, Santiago Calatrava, who much prefers a curve to a straight line. On the surface, his idea sounds very simple.
It has to be a building very versatile, you see, where small groups can work and all that. The idea was really to do a place very open, very transparent, and full of life.
The thing about Calatrava is his designs and specifications are incredibly complicated. This means engineers have to really think differently about the materials they're using and how they're going to build his vision.
From the Oculus Station House in Manhattan and Milwaukee Art Museum in Wisconsin to the Auditorio de Tenerife in Spain, Calatrava's gleaming white signature buildings are both stunning and phenomenally difficult to build. Florida Poly will be no different. Set on a 170-acre campus in the soft Florida marshland, Calatrava's design will see 5 vast lakes with curved walls created in a nod to its wetlands home. From the 6th, a gleaming white 162,000 square foot oval structure will rise. At its center, a ribbed and glazed auditorium roof, creating a vast atrium leading to 26 classrooms, labs, and studios. On its roof, 2 huge shades will move with the sun to protect the interior from the blistering heat. The perimeter will be ringed by a 39-foot high steel pergola, built to provide extra shelter from the intense Florida sun and high winds. Calatrava's creation will be unlike any building any university in the world has ever had.
It was going to require a team of people willing to do something new and push the limits of construction, because the limits of design were pushed as well.
What's more, they've got just 30 months to do it.
Students needed to begin classes at the start of fall semester.
There was no extension. They were opening August 14th, 2014. Everybody on site knew that. We made t-shirts up that said that. We got to get done.
The first task is to build a set of foundations strong enough for the huge structure. Not usually a problem, but this site is on acres of waterlogged soil.
The first time we visited, it was like marshlands. This area here was soft soil, silts. So the soil as it was not adequate to support the foundations for the building.
Usually when you build on soft soil, you hammer in piles till you hit solid bedrock, but not here.
The swamps of Florida are less than ideal. It's basically like trying to build on top of a massive key lime pie.
Florida is a place with a lot of marshland, and the hard rock or the bedrock, it's very deep, so we needed to find a solution.
The bedrock is up to 80 feet below ground, so traditional piling would be eye-wateringly expensive. The engineers, though, have a solution called vibro replacement.
Vibro replacement is a technique we use to improve poor base level conditions in areas like marshland and make it capable of load bearing.
It works like this. Holes 3 feet wide are drilled deep into the fragile soil and then filled with stones or gravel. Next, this filler is vibrated and compacted, which makes the ground as strong as solid bedrock.
When we're drilling into the ground, if there's any clays, if there's any roots, if there's any unsuitable soils as we're going down, it's being replaced with rock. It's just like concrete, more than enough to support this building.
The stone columns were completed, and it worked like a charm.
With a solid structure for the building to sit on, the team starts work creating the enormous concrete slab on top. Like every aspect of this build, it's far from straightforward.
The math and the geometry is very tough. It was a series of radiuses and rotations. I knew in my mind that it had to be perfect.
The plan is to cast 2 huge curving concrete beams which will link up to form the base. And on that, they'll then construct the building. Using a technique called formwork, they build a massive spider's web of steel reinforcement bars within huge curved plywood molds. Then they fill it with concrete.
Every 5 feet, we had a pin in the ground to make that ring beam perfectly form.
An error at this stage could have catastrophic repercussions.
We put coordinate points on every single element that's out here. The light poles, switches, toilets, everything that we did in this building had a coordinate point and a dimension to it off of a baseline.
With the huge concrete curves cast, the next challenge is overcoming Florida's weather. Because as they install the 43 aluminum cupola beams that will create the 250-foot-long roof, they hit a major problem. The afternoon summer temperatures are reaching 105 degrees, causing the metal to expand and changing the dimensions of the beams.
We would have to erect these cupola beams in the early mornings, and we couldn't go past 10:30 because they would heat up, and as we put them in and the members in between that brace them, they would heat up and they would go out of plumb. So we would have to stop, hold that brace where it was, and in the next morning or at nighttime, we would continue our erection so that they wouldn't be out of plumb. It's very complex, not only the geometry, but the heat in the cold.
Working through the night and early mornings, the beams are installed, ready for the next bit of Calatrava magic, glass physics.
The glass arrives in large dimensions, you see, and then the glass allows you with an adequate pressure to curve it and then fix it into the frame. It's very simple.
It's also something the team has never done before, to take an enormous flat sheet of glass and bend it into an exact curve, which fits the beams. Luckily, Calatrava has, in his previous buildings.
In his brilliance and in his experience, he taught us that you can bend glass. So we bent those glass panels in the field. So all that glass is under tension on the first and second floors all the way around the building, and we bent it to the geometry of the radius. How cool is that?
Calatrava's awesome glazed atrium is almost complete. Now he has one more demand of his engineering team.
As constructors, they knew the roof itself was a real challenge.
They have to stop the 22,000 square foot glass atrium from becoming a giant greenhouse.
Our roof is one big skylight.
With so much glass, how can they shield the building from Florida's super intense sun? Calatrava's solution is beautifully elegant, but unsurprisingly, highly complex to build and install. 94 movable aluminum shades will be placed above the roof, able to extend outwards by more than 60 feet. Sensors will control hydraulic pistons to open and close them, optimizing the amount of shade they provide to the atrium inside. And while controlling the solar gain, it will still allow in the beautifully cool morning and evening sun.
They can pull the roof, in a vertical position, but they can also hold the most convenient inclination of the two roof wings. The building itself can change its shape to deliver shadow down below.
This giant sunshade may protect the building from the sun, but can it withstand the greatest danger Florida's weather has to throw at it?
On the West Coast, you worry about earthquakes. On the East Coast, you worry about hurricanes.
Next, will it survive the weather? In Florida, construction of the new university building's incredible moving roof shades is underway. And the engineers there have to make sure it will survive the worst Mother Nature can throw at it.
You cannot ignore hurricanes. Unless you design for hurricanes, you have problems. Every element you see here, especially in the exterior envelope, is designed to withstand the hurricane wind forces.
They decide the solution is to fit sensors to the louvers, which detect wind speed. Anything over 25 miles per hour, and they should automatically retract. The team is ready to see if the system really does automatically retract in the wind, and whether it will track the sun. It's a tense moment for everyone.
I don't think any one person remained in the building. I think everybody came out to watch the arms move for the first time.
Everybody was waiting for it with anxiety. Is it going to work? Is it going to behave in the way it was designed to? It was exactly as it was planned, and it was a gratifying moment, actually, the first time you saw these things moving. And it was, great, this is doing what we're supposed to be doing. It was a sense of achievement for everybody at that point.
When they went up, we were like, holy moly, Batman. We high-fived it. We high-fived it. Trust me, we got it. We're part of something that's never been done in the world. This will be the only one. How cool is that?
The finishing touch is to surround the completed building on either side with water. They dig out the 5 remaining giant ponds and don't need any innovative technology to fill them.
They fill the ponds themselves. Rain and water runoff from the roads. They fill themselves. Pretty amazing.
And not the only thing that's amazing about the ponds.
We discovered in the ponds alligators. Nobody was thinking we will get alligators. But in Florida, these things are very common. And it's interesting to have some pieces of the local fauna.
Ahead of the official opening, Santiago Calatrava flies in to check on his building. Finished in his signature gleaming white, it's a massive moment for the man who designed it and the people who built it.
It was a lot of enthusiasm by these people, and certainly the quality of the building merged out of it.
There's no sharp angles. When a diagonal meets a vertical, usually, it comes at an angle, but the rounded corners everywhere. Chamfered edges, no sharp edges anywhere, and no visible construction joints.
He told all of the workers, thank you. He wept some. I saw some tears in his eyes, as there were mine, and I'm sure a lot of the workers. And all my workers are giving their heart and blood and soul into this. It's what a builder dreams of. When you're working with an architect of his caliber, that's the best feeling that I could ever have.
Right on schedule, 30 months after work started, Florida Poly's new flagship is ready to welcome students.
It's unusual. It is really something. You don't see anything else like this.
It's awesome. It's like, how did they do that?
It was one of the high points of my career, so I'm extremely proud to have been a part of it.
It does inspire me. I still can't believe I'm here.
16,000 cubic yards of concrete, 1,400 tons of steel, and 80,000 pounds of glass have been crafted by hundreds of workers to create a brand new architectural wonder for the world.
I proved to a world-class architect that we were able to deliver and execute something not only that is beautiful, but it works. I think the stars were aligned. It was a chance for us to take his art and build a building out of his art, because this is truly art.
For our next extraordinary building, we travel to Bilbao in northern Spain. I say building, but it looks more like several buildings, as if some challenging pieces of sculpture have fallen from the sky and against all odds landed in just the right place to create one single architectural masterpiece. Now that takes genius.
In 1991, the formerly prosperous docks in the northern Spanish city of Bilbao were down on their luck. But that was about to change. Because after years of decline, the city had decided to fund the building of a modern art museum right there.
Before the Guggenheim arrived, Bilbao was not on anyone's cultural radar.
This is the Guggenheim Museum in Bilbao. So extraordinary, it's described as the most important building of the time. So revolutionary, many said it couldn't be built.
There was a lot of skepticism about, can this be built?
It took pioneering computer tech combined with old school construction skills to make it happen.
They've essentially created a 33,000-piece titanium jigsaw puzzle.
Every piece had to fit perfectly on the inside and on the out. The Guggenheim in Bilbao is the mind-bending 250,000-ton building that revived a city and shocked the world. So, how did they build it? As the 20th century wound down, Bilbao's steel industry, once its lifeblood, had dried up, and the old city port had relocated, leaving behind a scar.
It had left all this left bank of the river close to the center of the city without any real use.
In the 1990s, the city came up with a bold plan for change. Fill the empty riverside space with something extraordinary. A building that can host world-class exhibitions, but that's also in itself a huge show of confidence, putting Bilbao back on the map.
The museum was meant to be the catalyst of that change. You cannot do this by small jumps. You had to do this by a huge leap forward. And this project provided that opportunity, I think.
To help Bilbao take this huge leap, they choose architect Frank Gehry, creator of some of the world's most extraordinary buildings.
If you want a signature building, Frank Gehry will not disappoint.
He's one of the only architects who is a household name. One look at Gehry's buildings, and you'll understand why. From Paris's Fondation Louis Vuitton to the Lou Rouveau Center in Las Vegas, Gehry's designs have changed the world. But the huge museum in Bilbao could be Gehry's masterpiece, if anyone can work out what's on his mind.
His first models, they were strange. It was difficult to understand exactly how they would work, but there was some sort of magic in them.
Gehry soon fuses the models to create a design for a single coherent but utterly extraordinary structure. The heart of the building will be a 165-foot-high central hall, constructed using a lightweight but super strong steel frame. A series of curved bridges, glass elevators, and stairs will connect 20 galleries spread over 3 floors. The exterior will be made up of huge, sweeping natural forms, turning the building itself into a sculpture. Finally, it will be clad in titanium, each sheet less than a millimeter thick, and every piece unique. It's a design no one has seen before, let alone built.
There was a lot of skepticism about, can this be built? Can this be built on time? Can this be built on budget? So we understood that it was going to be a challenge.
With a budget of around $90 million, Gehry's build team must be at their most innovative to pull this off.
It's quite complex from the point of view of construction. What the client wanted us to achieve here was to help Frank Gehry to design a world-class building. And that included many things like new shapes, new materials, things that had never before been done in architecture.
The Guggenheim is so complex that 2D blueprints weren't enough to communicate Gehry's vision.
Gehry's team turns to computer software programs used in airplane design to create a feasible technical construction plan.
They had to build a virtual 3D model of the entire building so that the engineers and the contractors knew what to do. Today, this is very common, but back in the 90s, this was revolutionary.
A design this complex, featuring tall towers and sharp angles, means the team has only one material in mind for the framework: steel.
Steel is very much used in buildings when you want to get speed and when you want to get industrial production. And it enables you to do this type of things. It's lighter than concrete. It makes a lot of sense.
The very industry that collapsed and created space for this museum is now needed to pull off producing the complex frames. Separate elements are parceled out to workshops around the city.
Frank Gehry has been able to design it, but we have been able to build it mostly with local elements.
These factories are used to building ships, not futuristic museums. With no two pieces the same, it's no easy task.
It's complex because of the shapes. Every member is a bit different from the others.
The construction crew assembled the series of interlocking triangles that make up the intricate framework and give the residents of Bilbao a first glimpse of what's to come.
This building has a beautiful steel structure that you cannot see. But once you could start looking at that steel structure, it was like the skeleton of a dinosaur suddenly coming up. I think that was the moment when we started to really appreciate the scale of the building.
The skeleton complete, they now need to clad it in a tough outer skin, one that will protect it from the weather, but that can be molded to fit the building's curves. Gary opts for a material more commonly used in aerospace, titanium.
When you think about it, cladding, an ever-changing and flowing material, has a lot more in common with aircraft making than traditional buildings.
The next challenge is that Gary's hand-drawn shapes mean installation of the cladding panels must be done in a precise order, and there are more than 33,000 of them.
They've essentially created a titanium jigsaw puzzle. That's fine on a computer, it's even fine on the factory floor. But then on site, a team have to somehow fit that all together.
Next, how will they pull it off? In Bilbao, Spain, work is underway to clad the new gallery, designed by one of the world's leading architects, in 33,000 individual pieces of titanium, each precisely fixed to the steel skeleton.
By bending, they produce this pillowy effect. When you look at it, it's like a pillow where it has these little holes. It doesn't really, but it's the way it reflects the light. So for being such a huge metal building, it looks very handmade, very human.
With the curves complete outside, work moves on to creating the elegantly flowing interior walls. Here the engineers turn to a system commonly seen in domestic house construction. Drywall fixed to a frame. Though here, of course, there's a twist.
Normally, drywall is always flat, just gypsum boards with a cardboard on both sides. It's not easy to bend. To bend it, you need to use a very thin drywall that can be somehow humidified and then bent.
The construction crew perfect a technique of using thin drywall, which they dampen and bend to create flowing forms that would have been immensely heavy if cast in concrete. It's not only lighter, but cheaper and quicker.
As far as I know, no other building has this type of complex shapes with drywall.
The next challenge Gary sets to the team is to construct a series of curved walls, some in glass and others in solid limestone.
A lot of the stone is carved in two directions. That is very, very complex to do. You need to carve each stone separately.
Too complex to cut the limestone by hand, the team turns to computer-controlled milling machines, normally used to shape metal.
It had to be manufactured by machinery that did not exist. The contractor had to acquire a milling machine that was for the aircraft industry and to adapt it to carve stone.
Bending the glass is too expensive. Instead, the engineers opt for an illusion to trick the eye.
There are some places in the building in which you see the glass curving. Well, it's not curved at all. It's a flat glass made with triangles to create that illusion.
The sculptural glass is the final component in a building that's about to take the world by storm. In 1997, 4 years after construction started, Bilbao's stunning new museum opens its doors, on time and on budget. The building more than fulfills its brief.
The Guggenheim was built to house great works, but arguably, the building itself outshines them all.
It has become an icon for the city of Bilbao because it has signaled the transformation that the city has lived through the last 30 years.
Since it opened, the museum has ignited a whole new cultural scene and now brings in millions of tourist dollars, all driving new business and creating jobs.
For the people from Bilbao, it changed completely the city. It was a great thing for us.
More than anything, figuring out how to build the Guggenheim didn't just put Bilbao back on the map, it redrew it.
With Manhattan real estate amongst the most expensive on the planet, designers of New York's hippest performing arts center came up with a genius space-saving solution. It uses a sophisticated version of what I call the elasticated waist trousers principle. If you suddenly find you need a little more space, then everything just expands. You can pack twice as much in while losing none of the comfort. Neat, huh?
In 2017, on a tiny pocket of Manhattan's West Side, New York City decided to build an enormous new arts venue.
We have a limited amount of real estate here, and we really needed to get the best bang for the buck.
A place so clever it can shapeshift to provide different venues for different shows.
Everything that underpins the idea behind the shed is complete flexibility.
A chameleon-like building that defies logic and sense, doubling in size at the touch of a button.
When you see that there's wheels at the bottom, you say, what? How?
The world's only arts and entertainment venue that rolls out the razzle-dazzle in the evening, then magically disappears before morning.
It's kind of like a supersized version of a trundle bed that you only take out when you have guests over.
A hybrid of giant railroad engineering, cutting-edge materials, and extraordinary vision. This is the Shed in Manhattan. So, how did they build it? New York has perhaps the most famous entertainment district in the world. Nearby are galleries and museums that combine to create a feast for anyone seeking a cultural hit. It's all been here for years. It's also perhaps just a little old-fashioned. But in 2012, just 1 mile west, an opportunity arises for something fresh. An ingenious new development is underway to create America's largest private residential development in history. Called Hudson Yards, it's being built on a huge new deck created to sit above an enormous railroad storage depot. Along with 18 million square feet of high-end living and working units, a small space is kept for a new super flexible arts center.
At the heart of it, they wanted to have a cultural center. The idea we had was that the Shed could be a commissioning center, a place where things are made and presented across all disciplines, so across performing arts, visual arts, popular culture. So it would be a place really that is for all types of creativity.
Despite a very modest footprint, the building also needs to be able to take big crowds. It's a big ask for a tiny space. But led by Elizabeth Diller, architects Diller, Scofidio, and Renfro come up with a radical design called the Shed. Really a tale of two buildings. One half will be a permanent structure, built onto one of the skyscrapers. 115 feet tall, this section will house 8 floors of permanent exhibition and performance space. But here's where the fun begins. This part will be completely encased in another structure, a huge steel shell that, despite weighing 4,000 tons, will be able to move out across the piazza, instantly doubling the size of the building and creating a 17,000 square foot multi-use performance space complete with climate control and state-of-the-art staging systems. It will be an incredible building with the ultimate flexibility the clients want. It also needs a big leap of faith.
I looked at this design and I kept turning it around going, there's very little it couldn't do. Let's make it happen.
In 2015, work gets underway on the fixed half of the shed. This is the easy part. It's built using a tried and true steel frame construction method, permanently fixed to the concrete slab. But then comes the hard part. The team has to figure out what they're going to build the 4,000-ton outer shell from, and how they're going to make it move. Even for the most experienced engineers, it seems like a crazy idea.
My first reaction had been to say, why would anybody want to do this? That's not practical, that's not possible. So I had to train myself literally to instead say, well, how can we best achieve that?
In search of inspiration, the team turns to commercial cargo docks.
A gantry crane is a crane that rolls in and out on two sides of the boat and is able to pick things off the side of the boat. So that technology is actually very influential in the design of the shed. When you think about the movable shell, it's the same idea of two wheels with a frame on top of it that rolls in and out over a fixed building or a boat.
The team decides to build the moving half of the shed using a 4,000-ton steel frame. And to make sure it's super strong and able to hold up to whatever is thrown at it, the architects settle on a design based on triangles, called a diagrid.
We have a series of these verticals and a series of intersecting diagonals that creates this overall structural form. And when we move it, we want it to be lightweight and we want it to be stiff. So this idea of a diagrid structure ticks all of those boxes for us.
The team may have a design for a super strong shell, but now they need to get it to move. Inspiration again comes from the gantry crane and its huge sets of motorized steel wheels, running on tracks embedded into the ground. But unlike a container port with its strict safety procedures, these need to be safe enough for the public to wander over. That means the tracks have to be both immensely strong to cope with the weight, but also very shallow.
Getting something that's straight enough, flat enough, stiff enough so that it doesn't deflect as the shed moves, this is really where all the magic happens.
At just 272 feet long, this super-sized railroad will be one of the toughest in the world. Its tracks are 6 inches deep, much the same as a normal train. But these have to move the incredible 4,000-ton load from the building above. So they're made 3 times wider and 5 times heavier to be strong enough to shift the shed. They also have to be perfectly installed.
The rails need to be constructed to very tight tolerances to make sure that the building doesn't lock up, because we are talking about moving a very heavy building over them.
The next big technical challenge is designing a completely unique wheel system that will run on these special tracks and spread out the massive load.
So a bogie is a pairing of wheels. This is a 4-wheel bogie, so there are 2 wheels side by side, and there are also 2 rails, so there's some depth to it. They came in as a pair, and essentially a crane came and lifted them and put them right exactly on the rails where they go. The maximum that one wheel is designed to handle is about 800,000 pounds. We don't know of anywhere else where these wheels exist in the world.
With the 6-foot wheels and oversized tracks in place, the next challenge is designing a system that will move the frame back and forth across the piazza. It needs to be powerful enough to move the entire structure, but also not be visible at ground level.
If you were to go to a retractable stadium roof for a sports facility, the motors that actually drive the wheels are located directly at the wheels. They're somewhat greasy, they're mechanical machinery. They can be fouled by the public if they were down there, so it's better to have them out of harm's way and in a secure location.
Their solution is to hide the motors up in the roof.
It's not unlike a baby carriage where we're giving it motive force up at the top, so all of that force essentially goes through the building and is translated down to the rolling wheels on the rails at the bottom.
To make the motors move the frame, they turned to the tried and tested rack and pinion system. This was first used on the Mount Washington Railway in New Hampshire over 150 years ago, so that its locomotives could easily climb the steep tracks. For the shed, they mount 12 electric motors under the frame. These then power the small rack and pinion system located on the roof of the fixed shed building, which in turn moves the frame.
It doesn't take a lot of power to actually move the object. You're really overcoming the initial friction, and then you're sliding the building out. So the equivalent power of moving the shed is roughly equivalent to 2 Tesla cars.
Some 20 months into the build, the moment arrives when the team will see if their calculations are correct. It's a tense moment. Will the Gliding Arts Center produce a stellar dress rehearsal?
The night before we moved the shed, there was a lot of trepidation.
The proof is in the pudding, and I was actually surprised at how quietly it moved the first time. Not a squeak at all. It was virtually silent.
That day when we moved it for the first time, it was slow in terms of the movement, but it was flawless as well. Everything went exactly as it was expected to go.
The next challenge is to create a weatherproof shell that's strong, lets in light, looks amazing, but also doesn't weigh an ounce more than it needs to.
One thing that was very important is we've got a moving building. We're trying to minimize the weight as much as possible.
So when it comes to the glazing, the team turns to a cutting-edge material rarely used in construction. Ethylene tetrafluoroethylene, or ETFE for short, weighs in at 1/100th the weight of glass.
ETFE is another product that has migrated from the aerospace industry and is now used for all sorts of large-scale covering.
The biodomes of the Eden Project in England and the Allianz Stadium in Munich both show how ETFE can be used.
Not only does this material have insulating properties, it's also super flexible to work with.
ETFE is a system that is made by inflating 2 panels of plastic with air on the inside. They're continuously pumped in with new air so that they don't start deflating or anything like that, and they're able to create this very ethereal look. And it allows the building to be lighter, and then it's easier to roll it.
38 months after construction began, it's a big moment for the architects and engineers behind this groundbreaking building. April 5th, 2019. There's first night nerves as the shed finally takes its spot in the limelight.
To see it delivered exactly as promised, that was a pretty big wow.
We took this basic, simple idea with all types of complexity and we developed it. And I'm proud of some of those technical challenges. The shed will always be very special to me.
It's taken 3 years of bold design and engineering and cost $475 million. But this theatrical masterpiece in motion has finally arrived on the New York art scene.
It represents the possibility for change, for adapting to the world that is changing. It's one of the most flexible spaces. There's very little it can't do.